Hello everyone, I'm Yiqun Wang. I'm glad to present our work, PET-NeuS Positional Encoding Triplets for Neural Surfaces. Reconstructing surfaces from multi-view images is a classic problem, and current neural surface reconstruction methods typically use pure MLP network to encode SDFs. Although these methods can reconstruct smooth surfaces, there is still room for improvement when it comes to reconstructing surface details. We propose a novel framework called PET-NeuS that enhances multi-view surface reconstruction by enabling greater expressiveness for encoding local features while effectively reducing the impact of noise interference. Our solution is as follows. We first integrate triplet data structure into neural implicit surface reconstruction framework. We then modulate triplet features using positional encoding. Finally, we utilize multi-skill self-attention convolution to produce triplet features. A triplet is a grid-based 3D structure, which is composed of three learnable feature planes. These planes are orthogonal to each other. To extract a feature at a 3D coordinate, we project it onto each of the three planes, interpolate its nearby features vectors, and concatenate them. A signed distance function is a powerful surface representation. It takes the 3D coordinate as the input and outputs the signed distance. We use triplet features and MLP to estimate the signed distance. We then follow HF-NeuS and compute the density value for the following volume rendering. While a greater expressiveness to encode local details is useful to better fit the input data, there is also less inductive bias towards a smooth surface because of the impact of noise interference. We propose to modulate triplet features using positional encoding. We explore the Fourier series decomposition of 3D neural implicit function. We found that sine and cosine waves from different dimensions x, y, z are entangled with each other through multiplications. We derive the function as a combination of sine and cosine functions and approximate implicit function with MLP with sine and cosine inputs. This approximation is directly applicable to our SDF function by utilizing an MLP that takes triplet features modulated by positional encoding as inputs, which can reduce the impact of noise interference. The positional encoding involves functions of different frequencies. To better match different frequencies, we propose to use multi-skill self-attention convolution kernels with different window sizes to perform convolution in the spatial domain. We take the output triplet features produced by the self-attention convolution and concatenate them all together with the original triplet features to form the final triplet representation for different frequency bands. This further increases the fidelity of the surface reconstruction while suppressing noise. Now we present the experimental result of PET-NeuS. For Nerf-synthetic dataset, we found the reconstruction of the bumps and the wheel holes of the Lego model and the grid of the MIC model to be particularly impressive. For detailed dataset, the reconstructed surfaces by PET-NeuS preserve fine-grained details. For instance, the holes between the eyes of the Buddha and the windows are more obvious. For CO3D datasets, the reconstructed fine-grained structures are a lot of better than what can be achieved with NeuS. Thank you for your listening. For more details, please refer to our project page.